In this video, we're continuing our discussion of ordinary differential equations, and we're considering solution methods for solving initial value problems, and in particular, we're going to talk about numerical accuracy in a revisited format. So numerical methods applied to the model problem x prime equals lambda x can often be written in the form shown here, where at time step n, xn is equal to x0 times sigma to the power n, where x0 is the initial value, and sigma is the amplification factor. So we have already seen that sigma is equal to 1 plus lambda h for explicit Euler, and sigma is equal to 1 over 1 minus lambda h for implicit Euler. So in contrast, the exact solution can be written as shown here. So we know that the solution to our model problem has an exponential form where x of t is equal to x0 e to the power lambda t. And for any time, t can be written as n times h, where h is the time step. So we can write this as x0 times e to the power lambda n h, and then we can just write this as x0 times e to the power lambda h, all to the power n. So comparing equation 1 and equation 2 can give us an idea of the accuracy of the method. So essentially what we're comparing is sigma to e to the power lambda h. As you can see in our previous equation we had for our numerical estimate that this is equal to sigma to the x0 times sigma to the power n. So we're comparing this quantity with sigma. So we can note that e to the power lambda h can be written as shown here using a series expansion. So e to the lambda h is equal to 1 plus lambda h plus lambda squared h squared over 2 plus lambda cubed h cubed over 6, etc. And we can call this equation 3. So we see that comparing sigma from explicit Euler with this e to the power lambda h, we can see that explicit Euler only reproduces the first two terms. So we get 1 and lambda h, but we don't get any of the next terms. For implicit Euler, we have sigma is equal to 1 over 1 minus lambda h, and we can actually write this as series expansion, which is equal to 1 plus lambda h plus lambda squared h squared plus lambda cubed h cubed, etc. And if we can compare this with the exact expression or the exact answer, we see that it also only reproduces the first two terms. So again, we've got the 1 and we've got the lambda h. We do have a lambda squared h squared, but it's not the same as what's in the equation 3 here. And we can recall from our initial introduction of these methods that both of these methods are second order accurate for one time step, and globally they are first order accurate. So using our new analysis of numerical accuracy, we can say that a method is of order alpha if its amplification factor matches all terms up to and including the lambda alpha h alpha over alpha factorial term in the equation 3 here. So for both of our methods, we only matched up to this term, which was the lambda 1 h1 over 1 factorial, so they are first order accurate globally. Now it's important to note that the order of accuracy is defined for the linear problem. Recall that the model problem is the linearized version of the problem. So we cannot look at the accuracy of the method for nonlinear problems in this way. So the order of accuracy derived in this manner should be viewed as the upper limit on the order, where the method may have a lower order of accuracy for nonlinear problems. So the order of accuracy that we just described relates to the amplitude of the solution. But for oscillatory solutions, the phase error can sometimes be more relevant, or we sometimes want to look at these two things, the amplitude and the phase error, independently. So for this purpose, we'll consider the model equation with the purely imaginary lambda. So let's consider the equation x prime is equal to I omega x. For example, consider an initial condition x0 is equal to 1 for simplicity. So the exact solution is x is equal to e to the power I omega t, which is an oscillatory solution with a frequency omega and a unit amplitude. With implicit Euler, we have that xn is equal to sigma n x0, where sigma is equal to 1 over 1 minus I omega h. We can multiply top and bottom by 1 plus I omega h, and expand this out and write this as shown here. So sigma is a complex number, so we know that it can also be written as a product of its magnitude and this phase factor. So sigma can be equal to the modulus sigma times this e to the I theta. And in this with this expression for sigma, we can see from here that the imaginary part is the omega h over 1 plus omega squared h squared, and the real part is the 1 over 1 plus omega squared h squared. So if we want to write our sigma as shown here, this we can say that sigma squared, or the modulus of sigma squared, is equal to the imaginary part squared plus the real part squared. So we can get the expression shown here, which can be simplified as shown here. So this can cancel out with the square here. And we know that this is always going to be less than 1, because this value is going to be positive, so the numerator is always going to be greater than 1. So when we divide, we're always going to get less than 1. The angle, theta, is the inverse tan of the imaginary part over the real part. So if we plug in our imaginary part and our real part, we see that this is the inverse tan of omega h. So with t is equal to nh, the exact solution is given as shown here. So we saw this already. Xn is equal to e to the I omega nh, which is which can be written as shown here. So e to the I omega h to the power n. And our numerical solution, xn is equal to sigma n, which is the modulus of sigma to the power n times this phase e to the I theta power n. So the phase error is found by comparing this omega h here with our theta. So the phase error is omega h minus theta, which is omega h minus inverse tan of omega h. And we can note that inverse tan of omega h can be expanded as shown here. So omega h minus omega h cubed over 3 plus omega h to the power 5 over 5, etc. So for implicit Euler, we reproduce only the omega h term. So the phase error is omega h cubed over 3, which corresponds to a phase lag. And you can see the difference in the sort of the concept of the amplitude error and the phase error for a general numerical solution. So here the solid line is the exact solution, and the dotted line or dashed line is a numerical solution, and you can see that it has some sort of amplitude error as shown here, as well as some phase lag in this case.